put your name on your quiz. This is Tech Math 2. And we're in section 13.5. And I hope 13.5 is a reasonable thing to do, so it gives us some challenge. And yeah, it looks like 13.5 has to do with inverse trigonometric functions. All right. So that's pretty cool. So if the sine function does that, what does the inverse sine function do? Well, the inverse sine function will do this. And then, but a function can only be a function if at any particular value of x, it only has one number. So I look at that graph and I say, wow, I'm in trouble. It looks like I have an infinite number of answers, which of course I do. So we go and we do what mathematicians do when it comes time to worry about things like that. And we say, okay, the arcsine function is only going to be defined from 90 degrees, minus 90 degrees to plus 90 degrees. From minus pi over 2 to plus pi over 2. And that way, I don't get into trouble. I'm going to be perfectly okay. And then I go and I do the same thing, and I look at the cosine function. So I draw a cosine function, and it goes up and down and up and down. And then I ask myself, what does the arc cosine function look like? And I say, well, that guy has to be at 1 when he starts, and he's going to go like this. And again, I've got a problem of I'm not a function anymore, so I'm going to have to define it on some interval. So I define it from 0 to pi. So the arcsine function, arc cosine function, is defined from 0 to 180 degrees, or 0 to pi. Okay, well that seems like a reasonable thing to do. And then in order to get it, I just put it in my calculator, so it shouldn't be much of a bother, right? And then on page 468, we see what our arctangent and arcsecants and other stuff look like, which are interesting. So the guys with fancier calculator than mine, which I didn't bother to bring today, can do arctangents and arcsecants. The rest of us, normal human beings, can't do those because our calculator doesn't do those things. Or arc cotangent. We only do arcsine, arctangent, arccotangent. Okay. So now we turn ourselves into a literature class, and we look at number 1, and we want to know what the equation y is equal to the arc sine of x means. Right? So we say, well, if I'm going to change that into English, how am I going to change it into English? Well, I'm going to say that y is the angle whose, I spell whose there we go, whose sine is x. So when I say y is equal to arc sine of x, what I'm saying is y is the angle whose sine is x. If I take the sine of y, I get x. All right, so I'll do it again. I'll look at number 3, because I'm supposed to look at number 3, and I say, well, I have y is equal to the arc cotangent of 4x, and I say, well, y is the angle whose cotangent is 4x. Oh, okay. Look at number 6, because we're there. Y is 1/2 the arc tangent of 3x. And I say, well, 2y is the angle whose tangent is 3x. All right. So now you say, well, wait a minute. Why is this a literature class all of a sudden? I thought this was a math class. Well, now that I know that 2y is the angle whose tangent is 3x, then I can come over here and say, oh, there's the angle right there. There's 2y. How do I get 3x out of it? You know? And well, if y is 3 and x is x, then that would probably work. No, it wouldn't. But anyway, that's what I'm going to end up doing later on in the chapter. Is I'm going to be using those words to draw pictures so that I can get what I'm supposed to get, whatever it might be. Okay, we'll turn the page, see if it gets worse. Solve the equation. All right, so we'll look at 8. Number 8. What am I supposed to be solving it for? Anybody know? Oh, for x. So y is equal to the tangent of 4x. So the arctangent of y is equal to 4x. X is equal to the arctangent of y divided by 4. All right, seems reasonable. Anything weird there? Number 12, other than saying arc something or another. Y is equal to 1/2 cosine 3x. 2y is equal to cosine 3x. The arc cosine of 2y is equal to 3x. X is equal to the arc cosine of 2y divided by 3. So I think we just found another way to add, subtract, multiply, and divide, right? Yeah, that's about all. 14. Look at 14. Y is 5/2 sine 2 over 3x. So 2/5y is equal to sine 2/3x. The arc sine of 2/5y is equal to 2/3x. Did it again. And then I got x is equal to 3/2 arc sine of 2/5y. Well, that seems reasonable. Find each of these values expressed in radians. Now, remember that we said the arc cosine function is only going to give us an answer between 0 and 180 degrees. So that's all we're looking for. And the arc sine function goes from -90 to +90. And the arc tangent function also goes from, we didn't say what it went from -90 to +90. So those are the intervals that we're looking for our answers in. We can't have an answer someplace else other than those places. Earlier in the problems we said we'll find answers between 0 and 2 pi. Well, that's a different situation. But now it's saying find the arc function. The arc function is defined on a particular interval. You can't go off that interval. So we'll look at number 20. And we have the arc cosine if I could spell arc cosine, of 1/2. And okay, this is where having our unit circle memorized helps out some, but we know that this is 60 degrees. Do we know that? Do we need to put it in our calculator to know it's 60 degrees? Probably not. Ben would have to put it in his calculator to know it was 60 degrees, but the rest of you wouldn't be a real problem, right? All right, number 23. And we could put it in our calculator and have it come up 60 degrees, except that someone would have their calculator in radians and it'd come up with some BS answer and they'd put the wrong thing down. Anyway, just, another arc cosine problem. I don't believe it. How did I do that? Arc cosine minus square root of 3 over 2. Well, we know that that's going to be a reference angle of 30 degrees because the cosine of 30 degrees is square root of 3 over 2. So this is going to be a 30-degree reference angle, but we're looking for a second quadrant answer because we're negative, so 180 minus 30 is 150 degrees. And our calculator could have told us that too. Number 24. The arc tangent of 1 over the square root of 3. And so we know that answer too, right? That answer is 30 degrees. We do? Do we know it's 30 degrees? Again, memorizing the unit circle at this point would be a really cool thing to have, but the tangent of 30 degrees is equal to the sine of 30 over the cosine of 30, right? And this is 1/2 over the square root of 3 over 2, which becomes 1 over the square root of 3. Okay, so from that we remember that 30 degrees is correct. All right, we'll do 27, and we'll write down 60 degrees and move on. No, we won't. We'll do more than that. Ben says that's all he needs is to know the answer. He doesn't really need to care how. Arc tangent of the square root of 3. Well, we remember that the tangent of 60 degrees is the sine of 60 over the cosine of 60, right? And this is square root of 3 over 2, and this is 1 over 2, and that becomes square root of 3. So, of course, the answer was obviously 60, and that's why I wrote down 60 to begin with. All right. Number 30. The arc sine is 1. Well, where's the arc sine going to be 1? Going to be at minus 90 degrees. So that would be okay. 270 degrees would be okay. All right. Do we need to do any harder ones than that? 36, I guess we need to do. All right, so we need the arc sine of 0.75. Oh, bummer. Look at this. I'm supposed to express all my answers in radians. Bummer. Now I read the problem. So I got to go all the way back to what I did, 14. All right, all the way back to 19. I didn't do 19. All right, so I got to express my answer in radians. So the real answer is pi over 3. And the real answer is 2 pi over 3. 2 pi over 3. No? 5 pi over 6. 5 pi over 6, says Ben. 5 pi over... No, it's not. Yeah, pi over 6, probably. Yeah, 5 pi over 6. All right. And this would be pi over 6. And this would be pi over 3. And, all right. And so now I'm doing 36. Oh no, this has to be minus pi over 2 or 3 pi over 2, either way. Either one is the same answer. Okay, now I can do 36, but my answer has to be in pi. Luckily, I have my calculator, and I can, I didn't think I had it there for a moment, and I can go to mode, and I change the radians. I don't have to be in pi, I just have to be in radians. So I'm in radians, and I want the arc sine of 0.75, and my calculator says the answer is 0.848. Does it say how many significant digits? No. 0.8481. Now I have four. Well, I can't have four significant digits because I don't have, only have two there. In fact, I'll probably round this up to 2. 0.85. There, that's better. All right. Is that all right? Now we get to do the fun things. Okay, so now we get to do number 40. And these are my favorite type of problems too, because it separates the men from the men. I want the tangent of the arc sine of 1 over the square root of 2. All right. So remember what we did in the first part of the problem set? We wrote the meaning of things. All right, so we have to get to the meaning of things. I want the tangent of the angle whose sine is 1 over the pi over 2. Okay, so that's the meaning of what I have there. Okay, so I got a triangle here, and it's a right triangle because why not, right? And I got some angle. Okay, now the sine of this angle theta is 1 over the square root of 2. What does that mean? That means the hypotenuse is the square root of 2, and this side is 1. That's what that means. Now, if this side is 1 and the hypotenuse is the square root of 2, what is the other side? Oh, the other side is, let's see, square root of 2 squared is equal to 1 squared plus the other side, we'll call it y, squared. 2 is equal to 1 plus something. So this side has to be 1 as well. Now I want the tangent of y over x. So the tangent of theta is 1 over 1, clearly implying the answer is 1. So the tangent of the arc sine of 1 over the square root of 2 is 1. There. And you probably saw those on, well, none of you guys took the SAT exam, right, or the ACT exam. But if you would have taken either the ACT or the SAT exam, you would have seen a problem like that on it, and that's, again, separates the men from the girls in that case. Okay. All right, so we'll do 42, because these are so much fun. Aren't these fun? Yeah. The sine of the arc tangent of minus 1. All right, so we want the sine of the angle whose tangent is minus 1. All right, so now we come up and we have this triangle, and we have this angle, and the tangent of theta is minus 1, so that means we've got minus 1 on that side divided by 1 on this side, because this is the y component divided by the x component, in which case this is the square root of 2 on the hypotenuse. Okay, so we want the sine of theta, which is going to be the side opposite, minus 1 divided by the square root of 2. And then we say, well, we really don't want to have a radical in the denominator. So for my final answer, I will write minus the square root of 2 over 2, and that'll be my final answer. So that was okay. Oh, well, we do 50. All right, number 50. We want to find the sine of the arc cosine, if I can spell arc, cotangent, of the arc cotangent. Way to go, I misspelled arc cotangent. All right, arc, the sine of the arc cotangent of 1.635. Okay, so I want the sine of the angle whose cotangent is 1.635. All right, so I got this triangle thing, and there's my angle, and if the cotangent is 1.635, that's x over y. So y could be 1, and x could be 1.635, in which case r would be the square root of 1 squared plus 1.635 squared. And I just find that number. Square root of 1 squared. I wonder if that's going to come up 1. Plus 1.635 squared. Close parentheses. So now I know the hypotenuse is 1.916. Okay. And then the sine of theta, which I'm looking for. So the sine of theta, which is going to be the y component over the hypotenuse, 1 divided by 1.916. And so I'm going to go and take 1 divided by the answer already in my calculator, and I'm going to find my final answer is 0.5218. Okay? So now you have a clue why we've done several chapters in trig, just so we could solve a problem like that, right? Otherwise, why bother, right? If we didn't have problems like that to solve, why bother? All right, so now we have to find algebraic expressions for each of these things. All right, so that's cool. We'll start with 51. So I want the cosine of the arc sine of x. All right, so I want the cosine of the angle whose sine is x. Okay, so I draw a picture, and I'm like that, and there's theta, and for the sine of theta to be x, this could be x, that could be 1. If that were the case, then this would have to be the square root of 1 minus x squared. And then I could say, well, the cosine of theta is going to be the x component, square root of 1 minus x divided by 1, in which case we wouldn't put a divided by 1 there, 1 minus x squared. Everybody knew that was a squared. How come somebody didn't tell me to square it? Okay, you all knew that was supposed to be squared, right? Yeah. But no one told me. All right, so see how I'm going to do that? But if I don't go and write this out in words, then there's no way I'm going to go from that expression to that picture. My mind doesn't work that way. And that is really sad to say. You know, it didn't even work that way when my mind was your age. That's even sadder to say. So I've always had to do that. All right, so 52. I want the tangent of the arc cosine of x. Okay, so I want the tangent of the angle whose cosine is x. So I draw a picture. There's some angle. If the cosine's x, then the adjacent guy can be x. That can be 1. If that's the case, then this side is 1 minus x squared. And then the tangent of that angle is the opposite, square root of 1 minus x squared divided by x, the adjacent. Okay. Do 56 next. We have the sine of the tangent, the arctangent of x. So I want the sine of the angle whose tangent is x. So I got some angle. Is that, now if the tangent is x, x can be that, this side can be 1, this side can be the square root of 1 plus x squared. And so I want the sine of that angle. And so the sine is going to be the opposite, x, divided by the square root of 1 plus x squared. Now, I've always said don't leave a radical in the denominator, right? In this case, we're going to leave it in the denominator. Now, why is that? Why is it that we always have to rationalize our denominators, and now we're not doing it?
Because that's really difficult.
No, it wouldn't. I can't rationalize that denominator. X, the square root of x plus x squared divided by 1 plus x squared. I could do that, right? I can rationalize the damn denominator. It's not that hard. But why do I say, well, we're not doing it anymore? All right, well, who told you to rationalize the denominator first?
Ninth grade teacher.
Yeah, your 9th grade teacher, your 8th grade teacher, your 7th grade teacher, somewhere around there. Well, they were dealing with things like this. That's what they were talking about. As your math gets more complicated, we go against our 9th grade teacher and say, this form is so much simpler than that form. Why am I complicating my form? Okay, and then so when you get to calculus, you're not gonna rationalize your denominator and do that. You're gonna leave it like it is, like that. You're still gonna rationalize this denominator when you get to calculus, but you're not gonna rationalize something like that. You're just gonna leave it that way. And when you get to differential equations, you're not even gonna rationalize this guy anymore. You're just gonna leave him like that. That's perfectly okay. Why would I want to change that? So have days like that. 58. So you have to remember, I said it first. If when you rationalize the denominator, it's going to be a more complicated form, don't bother. All right, so where was I? 58, and then we get to do something more cool. The sine of the arc sine of x. Okay, I'll let you guys work on that a little bit. You done yet?
Yeah.
X. Yeah, that's right. The sine of the arc sine or the arc sine of the sine. Either way, the arc sine of the sine of x is x2. You know, so these are inverse functions, and so I hope that one shows up on a test.
Me too.
Yeah, that'd be okay. I'd like that one. Well, I guess we ran out of time, and we can't do the graphing of 63, 64, and 65. Oh, darn. Yeah, that is really disgusting, I know.